So now we're here. So this is something to think about. What does E of X tell you? We'll try and do this little later. Maybe as I want to do some algebraic computations today, sort of finish off the technicalities. We'll come and discuss the intuition between E of X next class. Okay. So today's class, I want to start off with this. So I want to just sort of the next class. I want to just show the lemma. I want to show the proof of this lemma. That is, E of X is finite if and only if E of mod X is finite. It's kind of an important result, and it's very powerful. So, the subtle, it's kind of subtle to sort of understand, but the proof is kind of elementary. So, proof of lemma, what did I call it? 4.1.6. So, proof of lemma 4.1.6. So now, what does it do? So now we have to show E of X is finite if and only if E of mod X is finite. So let's say range of X is range of X is range of X is. So what happens? Then I define the range of mod X. So range of mod X. Think a little bit. What will it be? You have to be a little bit careful. Let me erase this thing. Rather than blue. Range of mod X would be what now? So you'd have to take everybody in T, but take its absolute value. So it's mod T such that T was in T. And that's the range of mod X. Right. Therefore, now you do E of mod X. You can go and find the distribution of mod X and do the whole thing. But if you don't know, as of now, we don't know anything about X. We just know X random variable. So let E of mod X would be the same as the sum from T. So let me call this as, let me erase it a little bit. Let me call this set as U, right, as a range of X, range of mod X. So it will be same as the sum over U and U, number U times the probability mod X is equal to. So now this is a simple exercise to just sort of conclude that this is the same as, or before that, we have to conclude now that try and see if E of X is defined as the sum from T in T, number T times the probability X. So we would have to sort of connect E of X with E of mod X. So we'd have to say if E of mod X is finite, then E of X is finite, and vice versa. That's the thing. These are definitions. These are definitions. So now I have to connect the two sums. So the trick is the following. So you have to do the reverse way. So here when we went to U to T, it was easy. Now let me define the little bit differently. So let me call it T hat as the set of all T in T such that mod T is in U. So I'm going the little reverse. Okay? I'm not going from T to U, but I'm going back from U to T. So now, since every U came from some T, T hat contains every element of T. So as as U and U came from some T in T, this will imply that T hat contains all of T. That's one observation you can make. So T hat contains T. Now, the next observation is the following. So for, let's say T is in T hat, and I'm writing in red, that way it's clear for you. So T is in T hat, and T is not in T. T is not in T. then this would imply that t is not in the range of x, right? T is not in the range of x. This would imply, what do you mean by t is not in the range of x for random variable? The crucial thing is it would imply that probability x equal to t would have to be 0, because x distributes all its probabilities on its range. So anybody outside its range takes probability 0. So therefore, what you could do is, even though t had a little larger set, you could extend, you could think of E of x as, it's okay because probability equal to 0. So I could just say this is a sum over t in t hat, t times probability x equal. That is done. Erase a little bit. So probability x equal. So there's two observations you can make. So let me rewrite this in red. So this t always is in red. So if t is in t and not in t hat, not t is in t hat, not in t, this is simple fashion. So E of x can be extended to t hat in this fashion because the rest of all zeros, so it's going to. So now you go the reverse way. So now you say, this is one computation you have to do. The second one is, you take a u and u, right? Take a u and u. You look at the event mod x equal to u, right? Look at the event mod x equal to u. Okay, mod x. What's that going to be? That's going to be the event x equal to u or x equal to minus. That's the event mod x. So then, and you know following fact, u is in t hat and minus u is also in t hat. This also you know, because u is in u and you know that u is in t hat and minus u. Observe. So let's observe. We have this. So therefore, therefore, u times probability mod x equal to u, right? That's just the above event. That's the same as u times probability x equal to u plus u times probability x equal to minus u. Let me just move this across. Let me just let me erase this. So now this is the same as this is minus u here. Sorry. No, I'll just put a u. Sorry. What am I doing? Let me start again. So use this. So same as u times the probability mod x equal to u is probability x equal to u plus probability x equal to minus u because you have two disjoint events. And that's the same as u times probability x equal to u plus u times probability x equal to minus u minus u, and that's the same as, I'll write it in this fashion. U is nu, so u is equal to mod u. So mod x equal to u, and u is nu, so the same as mod minus u. So probability x equal to minus u. This is one expression, and this is true even when u is 0, but I will not sort of. So this is, I'll write a small observation here. This is true even if u is 0. So it's true even if u is 0. It's a trivial equal. Both sound the same. So once you have this, you're in business now. Then you can relate the two sums. You have this observation here. Let's call this as maybe in blue, let's call this as double star, this inequality here, and this one here as a single star. So now you're almost ready to complete the proof. How do you complete the proof? You write the following. You write the fact that the sum over u in u times probability mod x equal to u. On this side, we know that's the same as we did the double star, u in u, such that your mod u times probability mod x equal to u plus mod minus u times probability x equal to minus u. So this is just a x here, not mod x. X equal to u plus mod of minus u times probability x equal to minus u, and that's the same as the chance of t in t hat. So then mod t, let me add this in red now. That's how you thought of t in t hat, we had mod t times the probability x equal to t. So add that in red again. I move to t hat. From t hat, I know exactly how to go to t. That's just the same as the sum on t in t mod t times mod of, that is mod of. So think of it as absolute value of t times probability x. That's the same thing. Sum is 0. But now I know, right? Now I know the fact that this is just, if this right hand side is finite, the left hand side is finite. So that just says that if e of x is finite, let's do if e of x is finite, this implies that the summation t in t times probability x equal to t converges absolutely, right? And that implies that the sum from t in t, the absolute value of t times probability x equal to t is finite, and that by this about triple star, let's call this triple star. So here I use triple star. So in triple star I used double star here, and I use star here. So by triple star, that's the same as the sum from u in u, u times mod probability mod x equal to u, and that means that e of mod x is 1. But now the same argument applies in reverse, because you know that you can do the same argument in reverse, because you know that e of mod x is finite. That implies that this guy is finite. So this guy is finite from the previous step. Black. But if this guy is finite from double star, I can go and say this guy is finite. But this guy is same as saying that guy can absolutely, and that means this guy is finite. So this is really this is a two-way inequality, and that's how one first solve it. So let me show the proof in one shot so that we can have a good view. Split view again. We go here. So let me come back here. Let me make this small. Let me go to the previous page. And let me come here. Let me put this down a little bit. So now the proof it's a little tricky, even though it's an elementary proof. You have to be a little careful when you count things. So what you do is you look at the range of x. You call that t. Then range of mod x, you call that u. Now you know that e of mod x is just summation u in u times probability mod x equal to t. You know summation t times probability x equal to t is same as e of x. Then you have to connect this range u with t, that you know one way. The other way is you take t hat, you look at all the elements in t, in capital T, whose absolute value is in u. Now, if T is in T hat, then and T does not belong to T, then so I should just I made one small error. Just, so that the way I defined T hat is not correct. So one small error. So T hat is all real numbers for which mod T is equal. So now if T is in T hat and T is not in T, then T is not in the range of X. So chance of X equal to T is 0. So therefore you take E of X is the sum from T in T hat, probability X equal to T times T. Because what's not in T will get 0 probability and it will just match up with the definition of E of X. So then you just do the reverse. You observe U in mod X equal to U splits up as mod U times probability X equal to U plus minus minus U times probability X equal to minus U. So once you have these two things, star and double star, on the second page on the right hand side, it's kind of obvious now. That you look at E of X, it splits up as two parts. So as if the sum converges absolutely, then what did I write R here? R came here also. Let me just remove the R. Okay, we'll come back and remove the R. So if we remove this R, there's no R here. Wait. So then the idea was that if you look at the right hand side, E of X was finite if the series converges absolutely, and the converge absolutely was just looking at the E of mod X because of this computation that we have done so far, up and down, T hat and U and T. That gives you the fact that E of X is finite means E of mod X is finite and vice versa. It's kind of a funky fact. I think it's important to do, but the proof is a little tricky, even though it's sort of you have to keep your head straight. Okay. Now let me try and sort of build on this. So I'll do one more algebraic fact today, and I'll stop. I'll come back and do the intuitive idea of expectations next time. So here's another theorem that is also an important theorem that we'll use again and again. We use quite. So this theorem. So here, suppose now I take two random variables. Suppose X and Y are two random variables, are discrete random variables. Both with finite expected value. And let's say we define on the same sample space. This system. So it's an important fact. Same sample space. Sample S, let's say. Stop. Let's say take two numbers, A comma B, be two real numbers. Then the following facts are. First thing is, if I take the expected value of the random variable A times X, that just gives me A times EX. The second thing is E of X plus Y will give me E of X plus E of Y. So the expectation is linear. And the third thing is that if I have, so of course this is a consequence immediate on this, is that X is non-negative, then E of X is non-negative. So now, of course, now each of these has to be understood in the following way. This equality is understood that both sides exist and are finite. Okay, only then the equality applies. If one side is not defined, you forget about the equality. Okay, so that's understood in that fashion. So in these two cases, let's call them a star. If both sides are well defined, that's when you understand this. Because it could be possible, of course, we show it cannot be. Suppose E of x, it could be possible that E of x is finite, E of y is finite, then E of x plus y is finite, then all this is true. It could be possible that E of x is minus infinity and E of y is plus infinity, and then x plus y might be defined, but this may not be, the equality may not hold true. So the equality only happens if both sides are right. Let me try and prove this theorem. So the first thing I have to show is, for proof of one, I have to show a times E of ax is a times E of x. So for that, let's say, so what I have to show? I have to show E of ax is a times E of x. So maybe I'll simplify the theorem a little bit, so that way the star may not be necessary. Let me suppose, so here I've said that with both finite expectations. That means I'll just say here, into this if, I'll just say both sides are automatically well defined. Also comes with the equality. So E of x. So first thing is I have to observe is that E of x is finite by definition, by assumption. So then let's say a is equal to 0. Let's say a is equal to 0. First, is a is equal to 0, a times x is also 0. And this implies in the previous lemma that E of 0 is just 0, which implies that E of ax is 0. And 0 is the same as 0 times E of x, because E of x is finite, so the thing is automatically just a times x. This part is clear. Now, let's say a is not 0. So let's say a is not 0. Let's do this case. So a is 0, the case is clear. If a is not 0, what happens? So a is not 0, then x is a function, let's say, from s to some number, let's say u. So you use the range of x. What will ax be? So the random thing, let's say y is equal to a times x. Y is an s from, let's say, t, where t is again the set of all a times u, such that u is the range of x. And now it's a simple idea, right? So E of y, which is what we want to understand, is the same as the sum from t in t, simple equality, t in t times probability y equal to t is the same as the sum from, just can rewrite this as the sum from, let's say, u and u, a times u, probability y is equal to a times u. That is by definition of elements in t. And then you come down and then you say, okay, oh, that's the same as the sum over u and u, a times u, and this is just the chance that I like that y is ax, a times x is equal to a times u. And now everything is finite, so I can add, multiply, remove. So the same as the chance that a comes out. And I have the sum. Sorry, the sum is in black again. The sum over u and u times the probability that here the a just cancels off, right? Excellent. And that's just a times. So this equality actually shows that that's just a times e of x. And if you observe, we start off with just a times x expectation excuse me, was just this simple proof. So if a is not 0, you look at y is equal to ax and just follow through the computation and get the answer. So that's pretty simple. So that finishes the proof that if y e of ax is equal to a times e of x. The next part is a little bit tricky, you'll be a little bit careful, even though it's again a simple part. So let's say this is where be a little bit careful. So now what you do is you want to show in the second part, you want to show e of x plus y is the same as e of x plus e of y. Then you want to show. So how do you understand the expression on this side? This side is you take z is equal to x plus y, and then you think of it as e of x plus y is the same as e of z, right? And it's the same as the sum from z of z, that is range of z times the chance that z is equal. Right? That's how you understand the right hand side. And these two you understand clearly. Right? These two you understand. So now somehow you have to show that these two are the same. So you have to, if you want to show this proof precisely, you have to go and compute the distribution of z. Somehow, once you find that out, you should better get this idea. So let's try and see how to do this. Let's try and see. This will take some amount of work. So the first observation is the following. What's the range of z? So let z equal to x plus y. Then the range of z is the same as, let's say, s plus t, where s is in the range of x and t is in the range of t. And that's just a function equality. The range just splits up as a sum. Maybe instead of s and t, let me use u and v. So because I'm using sample space as s. Let me say u plus v, such that u is in the range of x and v is in the range of y. That's how any element in the range of z looks like. So therefore, e of x plus y, so it's the same as, think of it as e of z, is the same as the sum over all z in the range of z times the chance that z is equal to z, little z. And that's what's going to be. That's going to be equal to. So you replace z by x u plus v. So it's same as the sum over all u in the range of x and all v in the range of y. The chance of, what do you just put? So z, you just put u plus v, right? And then you just put x plus y equal to u plus v. Or let's say, I'll just say x equal to u and y. That's how I'm splitting z out. Right? Let me just walk you through this again. Let me just come back and see. Let me just double screen up. Look at that. So what I did was I said I wanted to identify probability with z equal to z, and the way one does is you try and understand the range of z is just u plus v, for which u range of x and v range of y. Then E of z is going to be the sum over little z, chances z equal to z. But each z comes as u plus v, where u is range of x and v range of y. That means you can rewrite this sum as just u plus v, and you can now split up as x is u and y is v. That's the only way z will be u plus v. So once you do this splitting properly, you're on your way. Let me come back again. Let me go to the next page. So this is the same now as what now? As the same as the sum over u in the range of x, right? V in the range of y. I can split the two sums up. So in the following way. So I'll write it in this way. Since everything is finite, I can rearrange any way I want to rearrange. So I'll do this. Use u. I'll rewrite this as v in the range of y. I have u times the chance that u plus v times the chance that x equal to u and y equal to v. That's okay. So I can do all this because rearrangement is okay. As series converges absolutely. Otherwise, I can't do this. So that's the same as the sum over u in range of x. This now you can split up. So now you do this is the same as. So let me write this down as. I'll keep the u, right? I'll read it as probability x equal to u. So this I will move the v sum inside. So we will move the v sum inside. Sum plus I'll think of the other guy as a sum over v in the range of x, v in the range of y times v. Then I'll think of it in green. In green, I'll have to erase this guy. This is range of y. I'll just take out x. The sum over u in the range of x. And then this is just the chance that x is equal to u and y equal to u. Now I'm in business now. Now I know that if I sum over all values of y, the interval, I get the whole sample space. And they're all disjoint events. So the first thing becomes the sum over u in the range of x. So I should erase the green part. Equal to the sum over u in the range of x. This is u, and this whole thing is just the probability that x is equal to u. And here I have sum over the range of y, v times this whole thing is going to be a probability that y is equal to u. And why is that? Why is this is true? Why is this equality true? Write it down. Why is this true? This is true because we know this fact, right? We know that the event x equal to u is the countable disjoint union of v in the range of y. Let me write this in maybe this in blue. So this side is easy. X equal to u is the same as x equal to u and y equal to u. Right? That's just the same thing. That's why this sum is true. And also, and the reverse is true, right? The reverse is true. That is, if you take y equal to v, that's the same as the event where you take the union over all possible u in the range of x. Let me move this a little bit. U in the range of x equal to u and y equal to u. Right? That's just a fact, right? It's because this one. That's why you can just remove the sum of those. This equality is because of this. And these are disjoint events, and the countable union already sums up. So therefore, but then now you're done, because this guy is just the same. We go back to black. This guy is the same as E of x. That's the first sum, and then E of y is the second. So let me go back to my split screen. I have one comment to make before I finish the proof. So very good. We'll go around this one and make it small so you can see everything. Go back to this page. So here, there's one small thing I didn't sort of say. So at this step, what we should do is we assume that everybody is well defined. Okay, so we assume that to show this, we first assume that it's well defined. So let me erase that. I'll come back to this. I'll write this a little later. So in this step, you assume E of x plus y is finite, E of x is finite, and E of y is finite. So you assume that. So then you do this fourth calculation. So there's a small chance that, which I have not shown here, that if E of x is finite and E of y is finite, it could be that E of x plus y is not finite. But that's something that one can sort of work out and show that first that x plus y is a random variable. It will also have finite expectation. And that's because you can work backwards from the last equality and rearrange the sums to show that the series comes absolute. So modulo that small fact, I've sort of shown the fact that E of x plus y. Okay. Maybe I'll stop today. I'll come back and finish the proof for the second part, third part next.